Hello friends, in my this video I am going to discuss simple circuit to generate complementary clock. Okay, so suppose you have one particular clock signal. As you know, what is clock signal? Clock signal is basically one kind of square wave which is used to synchronize in a synchronous circuit or in digital electronics, so which has its own rise time and fall time, and it will oscillate in between VDD and 0 volt, right? This is although I have not drawn it properly, but it is one kind of clock signal, okay, which is very important in digital electronics or VLSI circuit design courses, obviously for synchronization purpose and to operate your sequential logic circuits and etc etc. So suppose you have this particular clock signal and you want to generate exact replicate complement of this particular clock signal. So when this input is low, the output of the complementary clock should be high. Then when the input of this particular clock goes to high, then the output should go to low. Then here see, in this particular input is high, so here in the complementary clock output should be low, and then again input goes to low so that your output goes to high. Okay, so this is one complementary clock, but exactly you have to make this complementary clock. Okay, that is the when the input goes from 0 volt to VDD, then the output goes should go from VDD to 0. When the input goes from VDD to 0, then the output should go from 0 to VDD, like that. Exact, like a replicate, like exact or replicate complementary clock you have to generate. Okay, how you can model this circuit? Obviously from the complementary clock name itself we can get an idea that okay, fine, I have one clock as input, so I will pass that particular clock through the NOT gate and I will take output of the complementary form in the output of the NOT gate, and then I have two complementary clocks. One is present in input side, one is present in output side of the NOT gate, right? So that is the simple approach. That is, suppose it is your system clock which is like this shape in nature. You pass through NOT gate, that may be made up of BJT inverter, that may be made up of MOSFET inverter, or that may be made up of CMOS or NMOS, whatever. So just you will take output in the inverted clock as output of the NOT gate, right? So in this way we can easily generate inverted clock from this particular input clock. Okay, and in this case we have two complementary clock sets as output. Okay, but see, here is one problem is there. See, when you pass something through the NOT gate, suppose the NOT gate is basically, suppose this particular NOT gate is CMOS inverter. Okay, there is PMOS and NMOS connected, as you know from the basic concept of VLSI. So the particular CMOS has its own propagation delay, right? Because there are gate capacitance are there and different MOSFET capacitance are there, source capacitance, drain capacitance, that will charge and discharge according to their time constant, which will introduce delay. So we will not get exact replicate inversion of this input waveform at the output side. Okay, so basically see, here I have shown the propagation delay of introduced by this NOT gate. See here, suppose this is your input clock. At this particular instant the input clock goes from low to high. Okay, but see output clock, so here input is 0, so output should be 1. But see, as soon as the input goes from low to high, then and there in that same time output is not going from high to low, it is taking some particular time TP, which is called propagation delay, okay, to go from high to low. Okay, this is introduced due to propagation delay of the particular NOT gate. Whether you are considering BJT inverter or NMOS inverter or PMOS inverter or CMOS inverter, whatever you make as inverter, obviously it will have its own delay. Okay, so that delay is TP or propagation delay. So we cannot say, just you consider this is input waveform and this is output waveform, which is plotted here in y-axis obviously voltage and in x-axis obviously time is plotted. So you cannot say these two are complementary clocks because there is a delay in between their transitions. Okay, but we want exact kind of transition, so this is not a answer to generate the complementary clock. Okay, So what we can do that, we can make certain circuit in which we can generate exact replicate version of complementary clocks that I am going to show you. But before that, two prerequisite concepts are required. One thing is there is double inversion or buffer action of inverter. Okay, see, very simple. In digital electronics you have already studied NOT gate. Now suppose you consider one NOT gate connected in the back side of another NOT gate. Okay, so as a result what happens, so two NOT gate in series combination you can say, and see, in the input side if we provide 0, then 0 will be inverted to 1 due to this particular NOT gate, and then again this one will be inverted by this particular NOT gate and it will get 0. Okay, so logic state re-inverted to original state. See, the second output of the output of the second NOT gate is exactly same as the first input, or if you consider this first input as 1, after one time inversion here you will get 0, then again 0 will be inverted, and in the output of the second NOT gate you will get 1. So whatever you provide as input in this particular NOT gate in the input side, the same state you will get as the output of the second NOT gate, because two times inversion is happening. As like you can intuitively understand, like this kind of action is happening, A complement equal to A, right? These things you have already studied in your digital electronics course. Same thing we are implementing here. A complement because of one time NOT gate, then again another inversion due to the second NOT gate, so A complement, so you will get A. So this is double inversion. This is one concept which is required to generate complementary clock. And one more very famous concept, that is transmission logic gate, which you already studied in detail in your VLSI course. See here, one PMOS and NMOS connected like this kind of parallel connection you can say, and here in the gate we are implementing complementary clock. Okay, so S bar and S we are implementing, that is suppose S we are implementing VDD in NMOS, we should implement 0 volt in the gate of the PMOS. Okay, because to turn on the MOSFET, you know, for NMOS we have to apply very high voltage in the gate, and for PMOS we have to apply low voltage. So with respect to digital electronics, you can assume like this, that S to turn on this transmission logic gate we should apply in S, we should apply, or in the NMOS we should in NMOS gate we should apply VDD, and in the PMOS gate we should apply 0 volt. Now if you apply that, so if you give your input as X and you are taking output as F, so see, if S equal to 1, that is if this particular NMOS gate is connected to VDD or high value, then see, F will be equal to X. Okay, that is whatever you are giving here, whether that is VDD voltage or 0 voltage, exactly that you will get in the output side. Okay, there is no attenuation like we got in pass transistor. Suppose you are considering NMOS pass transistor, then if you are providing VDD here, and if your NMOS is in on state, then you will get VDD minus VT, a certain threshold voltage amount drop you will get in pass transistor, right? So to overcome the effect of the attenuation in case of pass transistor, we use transmission gate, and if S is 0, that means NMOS gate is connected to 0 volt, so obviously NMOS will be off, and S bar is on, S bar is high. If S is 0, that means S bar is VDD or high value. So in PMOS you are implementing very high value in the gate, so obviously PMOS will be also off. So both S and S bar are off, so there is no connection in between left and right hand side. So F or output will be basically high impedance state you will get. Okay, so we are not interested in this particular part until and unless you are designing some certain circuits of in case of sequential or combinational logic circuit, then only you have to take care of this particular case. But suppose in the S we are implementing VDD and in the S bar we are implementing 0 volt, then obviously all the time this particular transmission logic will be on, and whatever in the output side, that will be passed to the output side as it is. If it is VDD will be passed itself. If it is 0 volt, 0 volt will be passed itself. Okay, so this is the beauty of the transmission gate. Using these two basic concepts, that is double inversion or buffer action using two inverters and using transmission logic concept, we can generate simple circuit to generate complementary clock, and that circuit is this one. Okay, see, I am going to explain the operation in detail, just try to understand. Suppose you provide your clock signal here. Okay, now the problem is to generate complementary clock. If you use single inverter, so what will happen, it has its own delay, so exact complementary action you will not achieve. So to avoid that, we are using this kind of configuration, and this is the simplest explanation or simplest model to generate complementary clocks. Okay, see what I have done. The clock signal I am applying here. Here this particular input clock is passed through two inverters. Okay, so as you know, these two inverters connected back to back means this is basically buffer, but also it will act like buffer, that is whatever input the output will be same, but obviously some delay will be there. So this particular clock you will exactly not get in the output, so this output clock of the second NOT gate is not equal to the input clock, so that I have denoted here clock in and this is clock. Otherwise I could define here, if these two NOT gate have no propagation delay, I could define here clock in itself, but see here I have not defined. This clock and this clock in are different, but those are almost in same nature. Just what is the difference? The difference is there is some delay in between this clock in and clock. Okay, and see, to generate clock complement, what I have done, I have implemented this one time inversion only, but first I have passed the clock in through one on transmission logic. Okay, see, the transmission logic gate is always on, because in the NMOS side we are implementing VDD, in the PMOS side we are implementing what? In the gate of the PMOS we are implementing 0 volt. So obviously this TG logic will always be on. The transmission logic in small form, it is also called TG logic. Okay, so whatever clock in, it will be passed to the output, and then we are inverting once, so we will get clock complement. So what is the advantage of implementing this circuit? See, if we implement one time inverter, we were unable to get exact inversion, but see here in this case we are getting a clock complement and clock, but see in between these two, the transition delay or the propagation delay which we were getting earlier, that difference in between transitions can be reduced in a very high or accurate amount. Why? Because this inverter delay can be compensated by this particular inverter, and this particular inverter delay can be compensated or nearly compensated by this particular TG logic, because the TG logic also itself has its own delay. Okay, so this particular inverter delay can be implemented in this particular clock complement case by using this TG logic. Okay, so this TG logic and inverter will produce one particular delay. That delay is almost equal to the delay produced by this particular two NOT gates. So as a result, this clock complement and clock will have almost exact complementary actions. So when the clock complement will go from low to high, in that almost same time the clock will go from high to low. Okay, so exact complementary action, to achieve that we have to use this kind of model. Okay, so this is all for this video. This is simplest circuit to generate complementary clock. I hope it is clear to you. In VLSI circuit design it is widely used. Okay, in interview also this may be asked. Suppose they ask you how you can generate complementary clock, and if you directly say that by simply using one NOT gate, then that answer will be wrong, because the very small amount of delay also will affect a circuit, digital circuit, a lot. Okay, so this you should have a clear idea in this portions, TG logics, propagation delay, like these concepts. Okay, so this is all for this video. Thank you for watching.